Welcome everyone, and thank you for joining us for our discussion on oligonucleotide production capacity improvement with PolarDry electrostatic drying technology. My name's Keith Krantz. I'm our Chief Operating Officer with Fluid Air. Fluid Air is a division of Spraying Systems company. We're headquartered in Naperville, Illinois, just outside of Chicago, where we have our main manufacturing facility and our main process laboratories. We also have laboratories globally to help support our international customers. While Fluid Air got its start with oral solid dosage processing equipment, today we want to discuss with you our PolarDry electrostatic drying technology. So when making powders, you traditionally have two methods, either lyophilization or spray drying. Now, spray drying is great for making mass quantities of powder on demand. However, due to the high temperatures needed for the process, it's typically not a good solution for temperature-sensitive materials such as bacteria, peptides, oligonucleotides, enzymes, or such materials like that. So in which case, lyophilization tends to be great at doing these types of products. However, it's a very slow process and a lot of times requires things like cryoprotectants to be added to your formulation. PolarDry was developed to cross the chasm between these two technologies and to provide the industry a way of getting that high demand product on demand without the degradation of high temperature and the loss of yield. Our patented process uses Spraying Systems Company's electrostatic spray nozzles to impart a light electrostatic charge to the droplets as they're being formed. This allows us to dry the particles in a much gentler fashion. If you look at the drying curves below, you'll see in a conventional spray dryer, typically that high temperature is going to create a shell around the outside of the particle. Once that shell is formed, you need to increase the temperature of the entire particle to be able to expel the liquid that's trapped inside. With our technology, we're able to dry the particle in a way that we don't need to get to those extreme temperatures. So looking at one of our dryers in the process, we start at the top where we have our 2-fluid atomizer that has an electrostatic charge that's creating the liquid droplets out of the feedstock. Those droplets are then exposed to the warm nitrogen drying gas as they travel into the drying chamber. That chamber has a removable flexible liner that we use to keep those particles from attaching themselves to the sidewall of the dryer, creating yield loss. As those particles will rapidly move through that process and get to the bottom where our high retention particle filters will separate those particles from the gas stream. We back pulse those filters periodically to make sure no particles are getting trapped in the filter and stay in the process. Those particles are then either collected in a vessel or in some cases removed with vacuum conveyance. The drying gas is then sent through a series of HEPA filters where we then dehumidify that gas and recycle it back into the process so we're not using just fresh nitrogen gas every time, causing higher utilities. So now that we've talked about the technology in brief, let's talk about its effects on oligonucleotide drying. So here you have a case where you have a temperature-sensitive material that's highly valuable. Thus, yield loss or damage to the product due to high temperature is not acceptable. So in this case, we'd like to show you how we can use the PolarDry technology to avoid these, yet still increasing the production demand. So with that, we can close and potentially stay for some questions. And I would like to thank you all for coming to our presentation. And any further questions, our contact information is on the screen, and we would love to see you at our prospective booths for any further discussions. Thank you.